Hi folks, we're going to take a look at page 157, number 17. So here we have a can that needs to hold 500 centimeters cubed of apple juice, so it's cylindrical. And it gives us a constraint on the height. It tells us the height must be between 6 and 15 centimeters. All right, and they want to construct it so that a minimum amount of material is used. Okay, and we think material meaning the outside of the can, so we're going to be working with the surface area. And they just give us this little, to make life easy for us, we assume that there's no waste. So we're using exactly the amount to create a cylinder. All right, so let's take a look at this here. So let me just draw a diagram, okay, just to kind of get ourselves started. So here's our cylinder, and of course we've got our radius and we've got our height, and they tell us that the volume of this cylinder has to be equal to 500. I suspect that'll come in handy. All right, and the thing that we want to optimize here is the surface area. All right. In fact, we're hoping to minimize that. And the formula for the area of a cylinder, which is 2 times the area of the base, so 2 times pi r squared. And then you imagine unfurling this, and you're going to get a big rectangle with the length being the circumference of that circle at the base, so 2 pi r times the height of the rectangle, which is just the height of the cylinder. All right, so there's the function that I have to optimize, and of course we've got 2 variables here, so we're going to have to write them in terms of 1 variable. All right, and that's where the constraint, this other constraint, is going to come into play. Is we know that the volume is 500, and we know that the volume of a cylinder is pi r squared h. All right, and so we need to isolate either r or h. And this is where we have a bit of a conundrum, because I really want to isolate h, because if I isolate r, it means, one of them is already an r squared. That's not a big deal, but it means I'm going to have to carry around a root here, which I'd rather not have to do. Problem is that the constraint that I'm given has to do with the height. So this is where I have to make a decision. Am I going to have to do a little bit of work to change these height values into radius values, or do I work with height as my variable, but then work with a square root in my equation? You know what? I just really don't want to work with a square root, so I'm going to solve for height. Okay. And I'm going to have to do a little bit of work. And, you can decide whether that was a good idea in the end, but this is how I'm going to choose to do it. So here, 2 pi r squared plus 2 pi r, and h is just 500 over pi r squared. The r in the numerator cancels out with one of those in the denominator, and the pi's reduce also. So I'm left with my area as being 2 pi r squared, okay, plus 1,000 over r. So quite a simple equation. But of course, now what I'm going to have to do is I'm going to have to change these height values into radius values. And that's where, again, I'm going to use my volume here. Okay, so I'm going to have to solve for radius. Okay, so that's just going to be 500 over pi h. Okay, and I'm taking the square root, and of course I'm only interested in the positive square root, and I'm going to have to change those height values. So I'm going to have to determine the radius when the height is 6 and the radius when the height is 15, and those are going to become my starting and ending values for my interval for radius. All right, so let's do that here. So we've got 500 divided by pi times h, which is the first one is 6, okay, and then take the square root, and that gives me 5.15. And then let's do the same thing for the other one. 500 divided by pi times, in this case here, 15, and take the square root of that, and that gives me 3.26. All right, so again, whether this was worth it or not, who knows, but this is where I decided to go. So I'm just going to say now that r has to be greater than or equal to 3.26 and less than or equal to 5.15. Notice here I'm approximating because I'm working on an application question. All right, And here they are saying inclusive, so means we are including the endpoint. So I'm working on a closed interval. Okay, so now we have our model with our domain. Let's go ahead and take our derivative. So this is just going to be 4 pi r, okay, minus, because this is 1,000 times r to the negative 1. So the derivative is going to be negative 1 times r to the negative 2. So we've done this many, many times that I'm not going to go through that whole process. And of course, I want to set this equal to 0. Okay, fairly straightforward rational equation. Multiply both sides by r squared. So I end up with 4 pi r cubed minus 1,000 equals 0. And so r is just, we'll bring the 1,000 to the other side, divide by 4 pi, and then take the cube root of that. All right, and that's our only critical point. So here, let's estimate that. So 1,000 divided by 4 times pi, and then exponent 1/3, and that gives us about 4.3. All right. So given that we're working on a closed interval, we know that the maxima and minima, the absolute ones, occur at either the critical points or the endpoints. So I'm just going to test A at 3.26, A at 4.3, the critical point, then A at 5.15, the other endpoint. And then here, let's see what we have. So we're going to stick it into our area equation. So I'll use this simplified form here. So we have 2 times pi times 3.26 squared, and then plus 1,000 divided by 3.26. And that gives us 373.5. All right, let's do the next one, 4.3. See how that compares. So 2 times pi times 4.3 squared. Okay, and then plus 1,000 divided by 4.3. And we get 3.348.7. So this one is smaller. Last one is we'll test 5.15. 2 times pi times 5.15 squared plus 1,000 divided by 5.15. Okay, and 360.8. So our minimum area occurs at the critical point. All right, so now let's go back to the question and see what they're looking for. And it says, how could the can be constructed so that use the minimum amount of material? So to me, that sounds like the dimensions, okay, because that's what you would use to construct it. So for our answer, we have that the radius would be equal to about 4.3 centimeters, and then the height is just equal to, and this is where I'll use my equation, 500 over pi times 4.3 squared, and let's see what that gives us. Okay, 500 divided by pi times 4.3 squared. All right, and we get 8.6 centimeters. All right, so let's just do a little recap here. So step number 1 was to get the model. Very easy because it was just the area formula for a cylinder. Use the constraint of the volume to write it in terms of one variable. The little hitch here is because I chose to write it in terms of radius because that's the easier function to work with. I had to take these constraints that were given as height values and turn them into radius values before I could continue. And because I was working on a closed interval, I just had to test the critical point and the endpoints to figure out which one was the smallest. Okay, now I'm not sure if you realized here that the height is exactly twice the radius, or in other words, the height and the diameter are exactly the same. Now that shouldn't be too surprising, probably something you've either seen in a question before or back in grade 9, that when there's when everything's made with the sort of same, there's nothing special about any of these sides or portions of this cylinder, that the optimal cylinder is the one where the diameter and height are equal. Now, of course, what would have changed things is had our domain been, say, something like from 5 to 7, then clearly that wouldn't have been the case, because our critical point would have not been part of that interval. Okay, so the max and mins would have occurred at one of the endpoints. All right, that's it for this one.